Hello and welcome to the walking talking topic on circle theorems, question number 4 with me, Mr. Barton. A beautiful question here, 4 marks, load of information going on, no need for reasons, but we're just going to say them anyway. Write down the size of these angles. So let's have a look. A, B, C, D are all on the circumference of a circle. EF is a tangent. AB equals AC, so those two lines are the same size, as can be seen by those little dashes. BCE is 38, ACD is 41. Okay, write down the size of BAC. Now, I always like to label what I'm trying to work out, so it's that angle there. Now, what do I know about that angle there? Well, this is the trickiest of the circle theorems. You've got a tangent there, FCE, and a tangent is meeting a chord BC. Now, the angle made by that tangent and that chord, that 38 degrees, is exactly the same as the angle made in the alternate segment at the top of that chord. I describe this to my students as that chord is making a triangle, and it's the angle at the top of that triangle which is equal to the angle between the tangent and the chord. So that angle there must be 38 degrees, the same as that 38 degrees. So 38 for the first bit. Angle A to B to C, so this angle here. Well, this isn't too bad because I've just got myself a nice isosceles triangle. I know it's isosceles because it told me the angles must be the same. So it's going to be 180 degrees, take off my 38. And I think that's going to leave me with 142 degrees, and then that's got to be shared between those two angles. 142 divided by 2, I think, is going to be equal to 71. So he's 71, and I might as well mark him on as 71 as well, just in case that's going to be important. Right, what about this? Angle A to D to C. Now, you might be tempted to say, well, that's 90 degrees because angle's in a semicircle. But that's a load of rubbish because that line there, A to C, doesn't go through the centre. It's not a diameter. So I can't be saying that at all. I'll mark on what I'm trying to work out. But what I do have is I've got ADCB being points on the circumference, so that's a cyclic quadrilateral, and angles opposite each other in a cyclic quadrilateral add up to 180. So if that's 71 opposite it, I've got 180 take off my 71, which, if my maths is right, I think that's 109 degrees. So he's 109 degrees there. Okay, and I've just got one more little bit that's popped onto the final page, and that is angle C to O to B. C to O to B. Flipping out. Well, there's a twist, because that's not even on my sheet. So I'm going to have to get my ruler, which has disappeared somewhere. Well, let's just use this rather fetching green one, and I've got to go from C to O to B. Now, how big's this angle? Well, it'd help if I were joining it up properly. There you go, C to O to B. What do we know about this? Well, one thing we can spot straight away is we've got C to O to B, and then C also goes up to A back to B. And again, if you know your circle theorems, the relationship between this angle there and that angle there is that the angle at the centre is double the angle at the circumference. So if the angle at the circumference is 38, the angle at the centre, I reckon, is going to be twice that. So instead of being 38, I think it's going to be 76 degrees. So the final one there, 76 degrees. I'll tell you what, if you can do that question, you know your circle theorems inside and out. They do not get much trickier than that.